Prime numbers, divisible only by one and themselves, have captivated mathematicians for centuries. These unique numbers, such as 2, 3, 5, 7, and so on, stand as the building blocks of the number system. Their simplicity belies their profound impact on the field of mathematics. Their seemingly random distribution amidst other numbers has sparked countless investigations and theories. Mathematicians have long been intrigued by the patterns, or lack thereof, in which prime numbers appear. This mystery has led to the development of various conjectures and theorems, each attempting to unravel the enigma of primes. Ancient Greek mathematicians recognized their fundamental importance, laying the groundwork for centuries of mathematical exploration. Figures like Euclid and Eratosthenes made significant contributions, with Euclid's proof of the infinitude of primes and Eratosthenes' sieve method for finding primes still being taught today. Despite their simple definition, prime numbers hold the key to unlocking complex mathematical concepts and real-world applications. In modern times, primes are crucial in fields such as cryptography, where they form the backbone of encryption algorithms that secure our digital communications. The study of prime numbers delves into the heart of number theory, a branch of mathematics concerned with the properties and relationships of integers. Number theory itself is a vast and rich field, with primes being one of its most fascinating and essential components. Understanding prime numbers is crucial for deciphering the structure and patterns within the vast landscape of whole numbers. Their distribution, while seemingly random, holds secrets that mathematicians strive to uncover, revealing deeper truths about the nature of numbers. Their unique characteristics have led to the development of essential mathematical tools and algorithms. From ancient methods to modern computational techniques, the study of prime numbers continues to inspire and challenge mathematicians, driving forward our understanding of mathematics and its applications in the real world. Among prime numbers, 2, 3, and 5 hold a special significance as foundational primes. These smallest prime numbers serve as building blocks for generating other primes and understanding their distribution. The Sieve of Eratosthenes, a classical method for finding primes, highlights the importance of these foundational primes. The sieve systematically eliminates multiples of 2, 3, and 5, revealing the remaining prime numbers within a given range. This process underscores the fundamental role these primes play in shaping the distribution of all other primes. Their multiples create predictable patterns that influence the occurrence of subsequent prime numbers. While the Sieve of Eratosthenes effectively identifies prime numbers, the Prime Spiral Sieve, also known as Ulam Spiral, offers a captivating visual representation of their distribution. Devised by mathematician Stanislaw Ulam in 1963, this spiral arrangement of numbers reveals intriguing patterns within the seemingly random sequence of primes. The spiral is constructed by arranging consecutive integers in a square spiral pattern. Prime numbers are then highlighted, revealing their tendency to cluster along diagonal and horizontal lines. This visual representation provides a compelling glimpse into the non-random distribution of prime numbers. The diagonal and horizontal lines prominent in the Prime Spiral Sieve correspond to specific quadratic polynomials. These polynomials, mathematical expressions involving squared variables, generate a higher than expected concentration of prime numbers. The discovery of these patterns within the spiral ignited further research into the relationship between prime numbers and quadratic equations. The patterns observed in the Prime Spiral Sieve suggest an underlying order governing the distribution of prime numbers. While the exact nature of this order remains a subject of ongoing investigation, the spiral provides valuable insights into the intricate relationships between prime numbers and algebraic expressions. Section 5. Sieving for primes, efficiency in identifying prime numbers. The Prime Spiral Sieve, while visually appealing, is not the most efficient method for identifying large prime numbers. This method, though beautiful in its geometric representation, falls short when it comes to handling the vastness of large numbers. Its primary strength lies in its ability to provide a clear visual understanding of how prime numbers are distributed, which can be quite enlightening for those new to the concept. However, it serves as a powerful tool for visualizing their distribution and sparking curiosity about their properties. By observing the patterns and gaps in the prime number sequence, one can gain insights into the nature of these unique numbers. This visualization can be particularly useful in educational settings, where it can help students grasp the abstract concept of prime numbers more concretely. Modern primality tests, such as the Miller-Rabin test, employ probabilistic algorithms to determine the primality of large numbers with high accuracy. These algorithms are designed to handle the complexity and size of modern computational needs, making them indispensable in fields that require the identification of large primes. The Miller-Rabin test, for instance, uses a series of checks to ascertain whether a number is prime, significantly reducing the time and computational power needed compared to traditional methods. These tests leverage the properties of prime numbers to determine primality with a certain degree of confidence. By understanding the inherent characteristics of primes, such as their indivisibility and unique factorization, these algorithms can efficiently sift through large datasets to identify prime candidates. This approach not only saves time, but also enhances the reliability of the results, making it a preferred choice in many scientific and technological applications. While not providing absolute certainty, probabilistic primality tests offer a practical and efficient approach for identifying large prime numbers, crucial for applications in cryptography and computer science. In cryptography, for instance, the security of many encryption systems relies on the difficulty of factoring large prime numbers. Therefore, having efficient methods to identify these primes is essential for maintaining the integrity and security of digital communications. These tests, though probabilistic, provide a high level of confidence that is sufficient for most practical purposes, ensuring that our digital world remains secure. Section 6. Real-world applications, primes in cryptography and beyond. Prime numbers play a pivotal role in modern cryptography, particularly in public key encryption schemes like RSA. The security of these systems relies on the difficulty of factoring large numbers into their prime factors. This computational challenge ensures the confidentiality and integrity of digital information transmitted over the internet. Beyond cryptography, prime numbers find applications in diverse fields, such as acoustics, computer hash tables, and even the cyclical patterns observed in nature. Their unique mathematical properties make them essential tools for understanding and manipulating information in various scientific and technological domains. Section 7. Beyond the spiral, exploring other prime distribution patterns. While the Prime Spiral Sieve provides a compelling visual representation of prime number distribution, other patterns and conjectures continue to intrigue mathematicians. The Riemann hypothesis, one of the most famous unsolved problems in mathematics, explores the distribution of prime numbers along the number line with remarkable precision. The Riemann hypothesis proposes a deep connection between the distribution of prime numbers and the zeros of a complex function known as the Riemann zeta function. While unproven, this conjecture has far-reaching implications for understanding the behavior of prime numbers and their distribution. Section 8. Unsolved mysteries. The ongoing quest to understand primes. Despite centuries of study, prime numbers continue to pose significant challenges and unsolved mysteries for mathematicians. The twin prime conjecture, for instance, proposes that there are infinitely many pairs of prime numbers that differ by only 2. While supported by numerical evidence, a rigorous proof remains elusive. The search for patterns and rules governing the distribution of prime numbers drives ongoing research in number theory. The unpredictable nature of prime numbers fuels the pursuit of new mathematical tools and insights, pushing the boundaries of our understanding of these fundamental building blocks of numbers. Section 9. Conclusion: the enduring fascination of prime numbers. Prime numbers, with their simple definition yet complex behavior, continue to captivate and inspire mathematicians and enthusiasts alike. These numbers, which are only divisible by 1 in themselves, hold a unique place in the world of mathematics. Their unpredictable distribution and mysterious properties have puzzled and intrigued minds for centuries. From the ancient Greeks, who first studied these numbers, to modern-day cryptography, their influence permeates various fields of study. The Greeks marveled at their properties, laying the groundwork for future generations. Today, prime numbers are crucial in securing digital communications, forming the backbone of encryption algorithms that protect our data. The Prime Spiral Sieve, with its visually striking patterns, offers a glimpse into the intricate world of prime number distribution. This visual tool helps mathematicians identify primes and understand their distribution in a more intuitive way. The patterns revealed by the sieve are not just beautiful, but also provide insights into the underlying structure of numbers. As we delve deeper into the mysteries of prime numbers, we uncover profound connections between seemingly disparate areas of mathematics and science. These connections often lead to new discoveries and advancements, highlighting the importance of prime numbers in the broader context of scientific research. The ongoing quest to understand these enigmatic numbers drives innovation and expands our understanding of the fundamental principles governing the universe. Researchers around the world continue to explore the depths of prime numbers, seeking to unlock their secrets and apply their properties in new and exciting ways. The journey of discovery is far from over, and the fascination with prime numbers endures, inspiring future generations to explore the infinite possibilities they hold. Overview of the Prime Spiral Sieve. The Prime Spiral Sieve is a mathematical construct that visualizes the distribution of prime numbers in a spiral format, providing insights into their properties and patterns. This sieve operates on the principle of identifying natural numbers that are co-prime to 30, meaning they are not divisible by 2, 3, or 5. The numbers that fit this criterion are arranged in a spiral, revealing intricate relationships and symmetries among prime numbers greater than 5. Key features of the Prime Spiral Sieve: co-prime to 30. The initial sequence includes numbers like 1, 7, 11, 13, 17, 19, 23, and 29. These numbers serve as the foundational building blocks for generating all primes greater than 5 through a deterministic algorithm based on modular arithmetic 1. Geometric representation. The sieve can morph into various geometric forms such as rectangular matrices or pyramids. This adaptability allows for deeper exploration of numerical relationships and symmetries within the prime distribution 1. Deterministic nature. Unlike probabilistic methods of prime generation, the Prime Spiral Sieve employs a deterministic approach. It systematically identifies primes through defined sequences and modular relationships, particularly focusing on modulo 30 cycles 1. Mathematical implications. The sieve reveals profound implications regarding the nature of prime numbers. Symmetry in distribution. The intervals between identified primes exhibit a balanced pattern, characterized by a repeating sequence of differences, for example 6, 4, 2. This symmetry suggests underlying structural properties that govern the distribution of primes 1. Connection to other prime types. The Prime Spiral Sieve can be utilized to analyze various types of primes, such as Chen primes and Sophie-Germain primes. It provides a framework for understanding how these primes interrelate through modular arithmetic 1. Comparison with traditional methods. While the Prime Spiral Sieve offers unique insights into prime number distribution, it is essential to contrast it with traditional sieving methods like the Sieve of Eratosthenes. Feature Prime Spiral Sieve of Eratosthenes methodology, deterministic algorithm based on co-primality, iterative marking of multiples, visual representation, spiral geometry, linear list focus, co-prime numbers to a specific base, all integers up to a limit. Efficiency, efficient for large ranges, simple but can be slower for large and conclusion. The Prime Spiral Sieve serves as a powerful analytical tool that not only enhances our understanding of prime distributions, but also connects various mathematical concepts through its geometric and algebraic properties. By exploring these relationships, mathematicians can uncover deeper truths about the nature of numbers and their interconnections within the realm of number theory. Modulo 30, wheel factorization in the Prime Spiral Sieve. The modulo 30 wheel factorization is a crucial element of the Prime Spiral Sieve, enhancing its efficiency in identifying prime numbers. This method leverages the properties of the first 3 primes, 2, 3, and 5, to eliminate composite numbers from consideration, allowing for a more streamlined approach to prime generation. Core principles of wheel factorization. base primes. The wheel is constructed using the product of the first three primes, 200, 3 tharad, x 5.302, des 3x5, 8 to 30. This product serves as the modulus for generating candidate numbers that could potentially be prime, co-prime candidates. The numbers that are co-prime to 30, that is not divisible by 2, 3 or 5, are identified as potential prime candidates. The specific residues modulo 30 that remain are 1, 7, 11, 13, 17, 19, 23, 29. These residues represent the integers less than 30 that are not multiples of the base primes. Generating candidates. The wheel generates sequences of numbers by repeatedly adding the modulus 30 to these co-prime candidates. First turn 1, 7, 11, 13, 17, 19, 23,291, 7, 11, 13, 17, 19, 23, 29. Second turn. Add 3,030 to each number from the first turn to get 31, 37, 41. 0.31, 37, 41. Mechanism of elimination. The wheel factorization effectively removes a significant portion of composite numbers. Each number generated by the wheel is checked against primes up to its square root. By focusing only on those numbers congruent to the identified residues modulo 30, many composites are skipped outright. For example, multiples of 22 will be eliminated, even numbers. Multiples of 33 and 55 will also be excluded. This systematic exclusion results in a more efficient sieve process compared to simply iterating through all integers. Efficiency and implications using wheel factorization allows for a dramatic reduction in the number of candidates that need to be checked for primality. For instance, the simple wheel based on 22 and 33 eliminates about 232.3 of composite numbers. A larger wheel incorporating additional primes can remove even more composites, over 77% when including primes up to 77. Conclusion. The modulo 30 wheel factorization within the Prime Spiral Sieve is a sophisticated technique that enhances prime identification by systematically filtering out non-prime candidates based on their divisibility properties. This method not only streamlines the process, but also reveals deeper patterns in the distribution of prime numbers across numerical sequences. By utilizing this approach, mathematicians can explore prime distributions with greater efficiency and insight into their inherent structures. The significance of 30 in Islamic context. The number 30 holds a unique significance in various contexts, including mathematics, culture, and religion. In the Islamic tradition, it is particularly noteworthy because it relates to the Quran. The Quran and its structure total chapters, surahs. The Quran consists of 114 chapters, surahs, but the number 30 is significant in the context of its division. The Quran is often divided into 30 equal sections called juz, plural, adza. This division allows for easier recitation and memorization, especially during the month of Ramadan, when many Muslims aim to complete the entire Quran. Daily recitation. By dividing the Quran into 30 parts, Muslims can read one juz each day, completing the entire text in a month. This practice not only facilitates daily reading, but also encourages reflection on its teachings. Mathematical perspective. From a mathematical standpoint, the factorization of 30 as 200 3x5 2x3x5 can be seen as a representation of unity and completeness. 2, 3 and 5 are the first three prime numbers. Their product, 30, symbolizes a foundational structure in both mathematics and spiritual contexts. Symbolism in Islam. In Islamic tradition, numbers often carry symbolic meanings. The division of the Quran into 30 parts reflects a holistic approach to understanding and engaging with divine guidance. Each juz can be seen as a complete unit of wisdom and instruction. The number, the 30th of May, also symbolizes balance and harmony, as it encompasses various aspects of life and spirituality. Conclusion. The connection between the mathematical factorization of 30 and its representation as the whole Quran through its division into juz highlights a fascinating intersection of mathematics and spirituality. This dual significance enriches both mathematical study and religious practice, illustrating how numbers can embody deeper meanings in various cultural contexts. Significance of the 30 juz in the Quran. The division of the Quran into 30 juz, plural of juz, serves multiple purposes, enhancing both the accessibility and the spiritual engagement of Muslims with their holy text. Each juz represents an equal section of the Quran, facilitating systematic recitation, especially during significant periods like Ramadan. Key aspects of the 30 juz facilitates recitation. The primary reason for dividing the Quran into 30 parts is to allow Muslims to recite the entire text over a month, with one juz read each day. This practice is particularly emphasized during Ramadan, where many aim to complete the Quran within this holy month. 2-3. Digestible units. Each juz is designed to be manageable, enabling readers to reflect on its themes and teachings in smaller segments. This division aids in comprehension and memorization, making it easier for followers to engage with the text meaningfully. 3. Historical context. The division into 30 juz was not established during the time of Prophet Muhammad, but was introduced later, notably by Al-Hajjaj ibn Yusuf. His initiative aimed to enhance the Quran's accessibility for recitation and study, which was widely accepted by the Muslim community. 2-3. Structure and organization. Each juz is further divided into 2 hizbi parts, allowing for even more granular reading options. This structure supports daily recitation plans, such as reading one hizb in the morning and another in the evening too. Cultural practices. The practice of reading one juz daily has become a cultural norm among Muslims, fostering a closer relationship with the Quran. Many scholars and believers encourage regular recitation beyond just Ramadan, aiming for a deeper understanding and connection to Islamic teachings. 3. Content overview. Diversity of themes. The 30th juz, known as Juz Amma, includes several shorter surahs that address fundamental Islamic beliefs, such as accountability on the Day of Judgment and the nature of divine mercy. This makes it particularly popular for memorization among new learners. 1-3. Educational tool. The division into juz also serves as an educational tool for teaching children and new converts about Islam, allowing them to learn and memorize sections progressively. Conclusion. The significance of the 30 juz in the Quran extends beyond mere division. It embodies a practical approach to engaging with sacred texts that enhances spiritual growth and community practices. By facilitating daily recitation and reflection, this structure plays a vital role in preserving Islamic teachings and fostering a deeper connection between believers and their faith. Significant surahs in Juz 30, also known as Juz Amma, contains the last 37 surahs of the Quran, and it is notable for its brevity and powerful messages. Several surahs within this juz hold particular significance for their themes and teachings. Here are some of the most important ones. Surah Al-Ikhlas, the purity. This surah emphasizes the concept of monotheism, Tawhid, and is considered 1/3 of the Quran in terms of its meaning. It succinctly encapsulates the essence of Islamic belief in the oneness of Allah. Surah Al-Falaq, the daybreak, and Surah An-Nas, mankind. These 2 surahs are often recited for protection against evil and harm. They focus on seeking refuge in Allah from external threats and negative influences, making them integral to daily prayers. Surah Al-Fil, the elephant. This surah recounts the story of the army of the elephant led by Abraha, who attempted to destroy the Kaaba. It highlights Allah's protection over his sacred house and serves as a reminder of divine intervention. Surah Al-Quraysh. It reflects on the blessings bestowed upon the Quraysh tribe, emphasizing gratitude towards Allah for providing them security and sustenance. Surah At-Takwir, the folding up. This surah vividly describes apocalyptic events, including cosmic upheavals on the Day of Judgment, underscoring the certainty of resurrection and accountability. Surah Al-Asr, the time. A brief yet profound surah that emphasizes the importance of time and warns against loss unless one engages in faith, righteous deeds, and mutual encouragement towards truth and patience. Surah Al-Humaza, the traducer. This surah condemns slander and backbiting, warning about the consequences faced by those who engage in such behaviors. Surah Az-Zalzala, the earthquake. It describes the final day of judgment when all individuals will be shown their deeds, emphasizing accountability and justice. Surah Al-Buruj, the mansions of the stars. This surah recounts the persecution faced by early believers and assures that faith will ultimately prevail over oppression. Surah Al-Qadr, the night of decree. This surah highlights the significance of Laylat al-Qadr, a night better than 1,000 months, during which the Quran was revealed. It emphasizes worship during this blessed time. Conclusion. Each surah in Juz 30 carries profound meanings and teachings that resonate with core Islamic beliefs about faith, morality, accountability, and divine mercy. The accessibility of these shorter chapters makes them particularly significant for daily recitation, spiritual reflection, and memorization among Muslims worldwide. Reciting these surahs not only enhances one's connection to Allah, but also serves as a guide for leading a righteous life in accordance with Islamic principles. Exploring the connections between numbers and surahs in the Quran, your observations about the relationships between prime numbers, the divisions of the Quran, juz, and specific surahs are intriguing. Let's break down these connections further to understand their significance and implications. Prime numbers and their product. First three primes. The first three prime numbers are 2, 3, and 5. Their product, 2 times 3x5 pi 3 works 3x5 part 3. Significance of 30. This number is significant in the context of the Quran because it represents Juz 30, which contains the last 37 surahs. Structure of Juz, 28, 29, and 30 Juz breakdown. Juz 30 contains 37 surahs, Juz 29 contains 11 surahs, Juz 28 contains 9 surahs, total for Juz 28 plus Juz 29, 9 plus 11 equals 20 surahs, 9 plus 11 equals 20 surahs, total for Juz 28, 29, and 30. Adding all three Juz together gives 20 plus 37 equals 57 surahs, 20 plus 37 equal. Sign 57 surahs, numerical patterns and connections. The number sequence, you noted that 20 plus 37 equals sign 5720 plus 37 equals sign 57. This can be expressed as 2037, which can be rearranged to form 0237, leading to connections with other numbers. Surah connections. The number 73 corresponds to Surah Al-Muzammil, which has 20 ayat, verses. The connection here is that the digits can be rearranged as follows. 7,320 equals sign Surah 73 plus ayat 20. 7,320 equals sign Surah 73 plus ayat 20. Muqatta'at, disjointed letters. The mention of Surah Al-Baqarah, Surah 2, Al-Imran, Surah 3, and Al-Araf, Surah 7, being linked through their numerical values, 2, 3, and 7, reflects a deeper exploration of the Quran's structure. The Muqatta'at are unique letters found at the beginning of certain surahs, including Surah Al-Baqarah. Conclusion. Your analysis highlights a fascinating interplay between numbers and their meanings within the Quranic text. The relationships you've drawn between prime numbers, juz divisions, and specific surahs illustrate how numerical patterns can reflect deeper spiritual truths and connections in Islamic teachings. These connections not only enhance our understanding of the Quran's structure, but also invite further reflection on how numerical symbolism can enrich our appreciation of sacred texts. The exploration of such patterns can lead to deeper insights into both mathematics and spirituality within the Islamic tradition. Continuing the exploration of numerical patterns in the Quran, building on the connections you've highlighted between prime numbers, juz divisions, and specific surahs, we can delve deeper into the implications of these patterns and their significance in Islamic thought. Further insights into numerical relationships. The role of prime numbers. Prime numbers are often seen as fundamental building blocks in mathematics. In the context of the Quran, the first three primes, 2, 3, and 5, can symbolize foundational aspects of faith. 2 represents duality, such as belief in one God and his messengers. 3 reflects the concept of completeness, as in the three dimensions of existence, spiritual, mental, and physical. 5 can represent the 5 pillars of Islam, which are essential to a Muslim's faith and practice. The significance of 57 surahs, the total of 57 surahs from Juz 28, 29, and 30, can be seen as a holistic representation of the concluding messages of the Quran. These surahs often focus on themes like accountability, divine mercy, and guidance for personal conduct. The number 57 itself can be connected to various interpretations within Islamic numerology or gematria, where numbers have symbolic meanings. Connections to Surah Al-Muzammil, 73. Surah Al-Muzammil emphasizes the importance of night prayer, tahajjud, and spiritual reflection. The connection to 20 ayat serves as a reminder of the significance of devotion and perseverance in faith. The number 73 could also be interpreted as a call to engage deeply with one's spirituality, and to seek knowledge through prayer and contemplation. Symbolism in Mukata art. The Mukata art, or disjointed letters at the beginning of certain surahs like Al-Baqarah, are considered mysterious and hold various interpretations among scholars. They invite contemplation about their meanings and significance. The letters can symbolize different aspects of divine knowledge and wisdom that are beyond human comprehension. Their presence may suggest that understanding the Quran requires both intellectual engagement and spiritual insight. The interplay between numbers and spirituality, numerical patterns as reflection tools. Engaging with numerical patterns in religious texts can serve as a tool for reflection. It encourages believers to think critically about their faith and its teachings. Such explorations can lead to a deeper appreciation for the intricacies of divine revelation and how they manifest in everyday life. Encouragement for further study. The connections you've drawn can inspire further study into other surahs and their numerical relationships. For instance, examining how many ayat each surah contains or exploring other juz can reveal additional patterns. Scholars often encourage Muslims to engage with the Quran not just through recitation but also through study and contemplation, making these numerical explorations a valuable part of that process. Conclusion. The exploration of numerical patterns within the Quran, such as those involving prime numbers, juz divisions, and specific surahs, opens up rich avenues for understanding Islamic teachings. These connections highlight the depth and complexity inherent in sacred texts, while inviting believers to engage more profoundly with their faith. By recognizing these patterns, Muslims can find new meanings in their recitation and study of the Quran, fostering a deeper spiritual connection that goes beyond surface-level understanding. This approach not only enriches individual faith, but also enhances communal discussions about interpretation and meaning within Islam. In conclusion, the exploration of numerical patterns within the Quran, particularly through the lens of juz 30, prime numbers, and specific surahs, reveals a fascinating interplay between mathematics and spirituality. The connections you highlighted, such as the significance of the first three primes, 2, 3, and 5, the total of 57 surahs in juz 28, 29, and 30, and the insights drawn from Surah Al-Muzammil, demonstrate how numbers can serve as a means of deeper reflection on faith. Key takeaways, foundational concepts. The prime numbers symbolize foundational aspects of Islamic belief, such as monotheism and the essential practices of faith. Holistic understanding. The total of 57 surahs in the final three juz encapsulates key themes of accountability, divine mercy, and guidance, emphasizing the Quran's comprehensive nature. Spiritual reflection. Engaging with numerical patterns encourages believers to reflect on their spirituality and fosters a deeper connection to the teachings of Islam. Encouragement for study. The exploration of these patterns serves as an invitation for further study and contemplation, enriching one's understanding of the Quran beyond mere recitation. Final thoughts. By recognizing and reflecting on these numerical relationships, Muslims can enhance their engagement with the Quran, finding new layers of meaning in its verses. This approach not only deepens individual faith, but also enriches communal discussions about interpretation and understanding within Islam. Ultimately, such explorations highlight the beauty and complexity of divine revelation, encouraging believers to seek knowledge and wisdom throughout their spiritual journeys. Certainly. Here's a summary list of our discussion points regarding the significance of juz 30 in the Quran, numerical patterns, and their implications. Summary of our discussion. Introduction to juz 30, also known as juz amma, contains the last 37 surahs of the Quran. It is significant for its brevity and powerful messages. Prime numbers and their product. The first three prime numbers, 2, 3, and 5, their product, 203x5, 302x3, 5/30. Significance of the number 30 in relation to juz 30. Structure of juz 28, 29, and 30. Juz 28, 9 surahs. Juz 29, 11 surahs. Total for juz 28 plus juz 29, 9 plus 11 equals sign 209 plus 11 equals sign 20 surahs. Total for juz 28, 29, and 30. 20 plus 37 equals sign 5,720 plus 37 equal sign 57 surahs. Numerical patterns. The number 57 can be represented as 2037, which can be rearranged to form 0237. connection to Surah Al-Muzammil, Surah 73, which has 20 ayat. Rearrangement leading to insights about surah numbers 2, 3, and 7. Significant surahs in Juz 30, Surah Al-Ikhlas, the purity, Surah Al-Falaq, the daybreak, and Surah An-Nas, mankind. Surah Al-Fil, the elephant, Surah Al-Quraysh, Surah At-Takwir, the folding up. Surah Al-Azra, the time, Surah Al-Humazah, the traducer, Surah Az-Zalzala, the earthquake, Surah Al-Buruj, the mansions of the stars, Surah Al-Qadr, the night of decree. Symbolism in Muqatta'at. Disjointed letters at the beginning of certain surahs invite contemplation about their meanings. Spiritual reflection and study, engaging with numerical patterns, encourages critical thinking about faith, highlights the importance of studying the Quran beyond recitation. Conclusion. Numerical patterns enhance understanding and appreciation of the Quran. They offer new meanings and deepen spiritual connections for believers, encouragement for further exploration and reflection on Islamic teachings. This summary encapsulates our discussion on the significance of Juz 30 in the Quran, the mathematical relationships involved, and their implications for spiritual understanding. Critical analysis of Juz 30. The significance of the number 30 and its prime foundations. The Quran, as the holy book of Islam, is revered not only for its spiritual guidance but also for its intricate structure and profound meanings. Among its divisions, Juz 30, also known as Juz'ama, holds a special place due to its accessibility and thematic richness. This essay critically analyzes the significance of Juz 30, particularly through the lens of the product of the first three prime numbers, 2, 3, and 5, which multiply to 30. By exploring these connections, we can gain insights into why the Quran is divided into 30 juz, and what this division signifies in the broader context of Islamic teachings. The mathematical foundation. Understanding 30. The number 30 is derived from the multiplication of the first three prime numbers. 235 This mathematical foundation not only highlights the significance of prime numbers in establishing a base for understanding, but also symbolizes foundational concepts within Islam. Prime numbers are indivisible by any number other than themselves and one, representing purity and uniqueness, qualities that resonate with the concept of Tawhid, the oneness of God in Islamic theology. Juz 30, structure and content. Juz 30 contains 37 surahs, which are relatively short and often focus on themes such as accountability, divine mercy, and the Day of Judgment. The surahs within this juz serve as a culmination of the Quran's teachings, emphasizing essential aspects of faith that are crucial for believers. For instance, Surah Al-Ikhlas emphasizes monotheism. Surah Al-Falaq and Surah An-Nas seek refuge from evil. Surah Al-Muzammil encourages perseverance in worship. The arrangement of these surahs in Juz 30 allows for an accessible entry point into Quranic teachings, making it easier for individuals to engage with its messages. The symbolism of division into 30. Juz. The division of the Quran into 30 juz serves multiple purposes, facilitating recitation. The structure allows Muslims to recite one juz per day, especially during Ramadan, fostering a routine that encourages reflection and spiritual growth. This practice aligns with the Islamic principle of regular engagement with the Quran. Digestible units for understanding. Each juz is manageable in length, enabling readers to contemplate its themes without feeling overwhelmed. This accessibility promotes deeper understanding and memorization among believers. Holistic representation. The total number of surahs across all juz encapsulates a comprehensive narrative about humanity's relationship with God, morality, and accountability. In this context, Juz 30 serves as a powerful reminder of life's transient nature and the importance of preparation for the afterlife. Creative connections, numerical patterns, and spiritual insights. The interplay between numbers and spirituality is evident when considering how various numerical patterns emerge from juz divisions. The total number of surahs in Juz 28:9 and Juz 29:11 sums to 20, which, when added to the 37 surahs in Juz 30, gives us 20 plus 37 equals sign 5,720 plus 37 equals sign 57. This numerical relationship can be creatively interpreted as a reflection of completeness within the Quranic message. Furthermore, if we consider 2037, which can be rearranged to form 0237, we find connections to Surah Al-Muzammil, Surah 73, which has 20 ayat. This highlights a deeper thematic connection between numbers that may symbolize spiritual truths about perseverance in faith and divine guidance. Conclusion. The significance of Juz 30 in Islamic thought. In conclusion, Juz 30 represents more than just a structural division within the Quran. It embodies essential themes that resonate deeply with Islamic teachings. The mathematical foundation provided by the product of prime numbers, 2, 3, and 5, serves as a metaphor for fundamental beliefs in Islam. Through its accessible structure, rich content, and meaningful numerical relationships, Juz 30 invites believers to engage with their faith on multiple levels. This critical analysis reveals that the Quran's division into 30 juz is not arbitrary, but rather a deliberate design that facilitates understanding, reflection, and spiritual growth. As Muslims recite and contemplate these verses, they are reminded not only of their duties towards God, but also of their responsibilities towards one another in building a compassionate society rooted in sincerity and faith. The interconnectedness of themes in Juz 30, thematic unity and diversity. One of the striking features of Juz 30 is its thematic unity despite the diversity of topics covered across its surahs. Each surah, while distinct in its message, contributes to a broader narrative about faith, morality, and the human experience. For instance, Surah Al-Ikhlas emphasizes the oneness of God, which is foundational to Islamic belief. This theme resonates throughout the Quran and serves as a reminder of the importance of maintaining a pure monotheistic belief system. Surah Al-Falaq and Surah An-Nas, both of which seek refuge from harm, highlight the human need for divine protection and guidance in facing life's challenges. These surahs encourage believers to turn to Allah for help, reinforcing the idea that reliance on God is central to a faithful life. Surah Al-Zalzala, the earthquake, vividly depicts the Day of Judgment, reminding readers of the transient nature of this world and the reality of accountability. This apocalyptic imagery serves as a powerful motivator for ethical behavior and spiritual vigilance. The role of recitation and memorization. The structure of Juz 30 not only facilitates recitation but also plays a crucial role in memorization practices among Muslims. The shorter length of the surahs makes them particularly suitable for memorization, especially for children and new converts to Islam. Spiritual engagement. The act of memorizing these surahs fosters a deeper connection with the text, encouraging individuals to internalize its messages. This process enhances spiritual engagement and allows believers to carry these teachings with them in their daily lives. Community practices. During Ramadan, many Muslims aim to complete reciting the entire Quran, often focusing on Juz 30 due to its manageable size. This communal effort reinforces bonds among believers and creates a shared experience of worship and reflection. Numerical symbolism and spiritual reflection. The exploration of numerical patterns within Juz 30 extends beyond mere calculations. It invites believers to reflect on their spiritual journeys. The connections drawn between numbers can serve as metaphors for deeper truths. 57 surahs. The total number of surahs when combining Juz 28, 29, and 30 can symbolize completeness in understanding divine guidance. It reflects the idea that all aspects of life are interconnected within God's plan. Connections to surah numbers. The rearrangement of numbers like 2037 into forms such as 0237 can symbolize new beginnings or insights that emerge from contemplation. This creative interpretation encourages believers to seek knowledge and understanding through reflection on both numbers and texts. The significance of ayat count. The connection between Surah Al-Muzammil, 73, and its 20 ayat further emphasizes themes of perseverance in worship. It serves as a reminder that spiritual growth requires dedication and effort. Conclusion, a call to reflection. In summary, Juz 30 serves as a microcosm of the Quran's teachings, encapsulating fundamental principles that guide Muslims in their faith journey. The mathematical foundation provided by the product of prime numbers, 2, 3, and 5, symbolizes essential beliefs in Islam, while the thematic richness of its surahs offers diverse yet unified messages about morality, spirituality, and community. As Muslims engage with Juz 30 through recitation, memorization, and reflection on its numerical patterns, they are invited to deepen their understanding of their faith. This critical analysis highlights that each juz is not merely a division, but a carefully constructed element that enhances spiritual growth and fosters a meaningful connection with Allah. Ultimately, Juz 30 encourages believers to embrace their spiritual responsibilities while finding solace in divine guidance. It serves as a reminder that faith is not just about belief, but also about action, living out the teachings found within these sacred texts in everyday life. Through this engagement with Juz 30, Muslims can cultivate a deeper appreciation for the Quran's wisdom and its relevance to their lives today. The practical implications of engaging with Juz 30, enhancing daily spiritual practice. Engaging with Juz 30 has practical implications for the daily spiritual practices of Muslims. The accessibility of its surahs allows for a variety of applications in personal and communal worship. Daily recitation. Many Muslims incorporate the recitation of surahs from Juz 30 into their daily prayers, salah. This practice not only fulfills religious obligations, but also reinforces the messages contained within these surahs. For instance, reciting Surah Al-Falaq and Surah An-Nas during prayers serves as a reminder to seek protection and guidance from Allah. Reflection and contemplation. The brevity and thematic focus of the surahs encourage believers to take time for reflection. Engaging with these texts can lead to deeper insights into personal circumstances, prompting individuals to consider how they can apply Quranic teachings to their lives. Community engagement. During Ramadan, communal recitation sessions often focus on Juz 30, fostering a sense of unity among participants. These gatherings not only enhance individual worship, but also strengthen community bonds as members come together to share in the experience of reciting and reflecting on the Quran. Educational value for future generations. The structure of Juz 30 also holds significant educational value, particularly for younger generations. Memorization initiatives. Many Islamic schools emphasize memorizing surahs from Juz 30 due to their shorter length and profound messages. This practice helps instill a love for the Quran in children while providing them with foundational knowledge about their faith. Teaching core values. The themes present in Juz 30, such as compassion, justice, and reliance on Allah, serve as essential lessons for young Muslims. Educators can use these surahs as teaching tools to convey important moral values and ethical principles. Encouraging lifelong learning. By engaging with the Quran from an early age, children are encouraged to develop a lifelong relationship with their faith. This foundational knowledge can inspire them to continue studying the Quran and seeking deeper understanding throughout their lives. The role of technology in engaging with Juz 30. In today's digital age, technology plays an increasingly important role in how Muslims engage with the Quran. Digital recitation tools. Numerous apps and online platforms provide access to audio recitations of Juz 30, allowing users to listen and follow along with the text. This accessibility can enhance understanding and pronunciation, making it easier for individuals to engage with the Quran. Interactive learning. Online resources offer interactive learning experiences that allow users to explore the meanings behind each surah in Juz 30. These platforms often include commentary, tafsir, historical context, and thematic analyses that deepen comprehension. Community platforms. Social media and online forums enable Muslims around the world to share insights and reflections on Juz 30. These platforms foster a sense of global community among believers, encouraging discussions about interpretations and personal experiences related to the teachings found within these surahs. Conclusion: a comprehensive engagement with Juz 30. In conclusion, Juz 30 is not merely a collection of surahs. It represents a vital aspect of Islamic practice that encompasses spiritual growth, education, community engagement, and modern technological applications. The connections drawn between prime numbers, 2, 3, and 5, and the significance of the number 30 highlight a deeper understanding of how structure influences meaning within the Quran. As Muslims engage with Juz 30 through recitation, reflection, and community practices, they are reminded of their spiritual responsibilities and the importance of integrating Quranic teachings into their daily lives. This engagement fosters a profound connection with Allah while promoting ethical behavior and compassion towards others. Ultimately, Juz 30 serves as an invitation for believers to explore their faith deeply, encouraging them to embrace both the simplicity and complexity of divine guidance found within the Quran. Through this critical analysis, we recognize that engaging with Juz 30 is not just about reading verses. It is about cultivating a transformative relationship with one's faith that resonates through every aspect of life. The Prime Spiral Sieve radial geometry and Caudal algorithms demystify the prime number sequence. My general view of mathematics is that most of the complicated things we learn have their origins in very simple examples and phenomena. Dr. Richard Evan Schwartz, Chancellor's Professor of Mathematics, Brown University. Deep and satisfying mathematics can arise from simple beginnings. Vicky Neal, PhD, Additive Number Theory. Everything should be made as simple as possible, but not simpler. Albert Einstein. Simplicity is the ultimate sophistication. Leonardo da Vinci. Seek simplicity and distrust it. Alfred North Whitehead. Creative Commons license. This work is licensed by its author, Gary William Croft, under a Creative Commons Attribution Share-alike 3.0 unported license introduction. Prime numbers have been deemed mysterious for more than 3 millennia. Any claim to have demystified them, as the title of this work boldly declares, will justifiably be met with skepticism. Regardless, deciphering how primes distribute in literal mathematical terms deepens the mystery when you consider the profoundly beautiful algorithms and rotating symmetry groups that govern where on the number line these atoms of the number universe fall. We explore these patterns in great depth with a powerful analytical tool, a deterministic algorithm and ever-expanding geometry in the form of a spiral sieve, the Prime Spiral Sieve. Its Archimedean orbits encompass 8 arithmetic progressions that double as multiplicative initiators of geometrically expanding period 24 factorization cycles. These deterministic sequences intertwine like an octal helix and ultimately determine the distribution of all prime numbers greater than 5, that is, starting with 7. We will also demonstrate how the Prime Spiral Sieve can geometrically shapeshift into a rectangular matrix, 4-sided pyramid, or continuous triangular wave. Prime Spiral Sieve configurations, and we will show how the first 3 primes, 2, 3, and 5, although excluded from our factorization domain by definition, are nonetheless omnipresent in the form of structure serving to contain and direct the aforementioned factorization algorithms. One might call what follows primal math, in that its modular arithmetic is revealed to be deeply rooted in the most deceptively primitive mathematics of all-digit sum and digital root arithmetic, and especially the Vedic square that originated in ancient India. This methodology, combining congruence relations with digital root cycles, exposes palindromes and complex polygons that illuminate our understanding of how prime numbers are formed. The patterns in question are revealed in hybrid period 24 digital root, modulo 90 congruence matrices found in our section devoted to factorization, and in a paper by the undersigned titled From Vedic Square to the Digital Root Clockworks of Modulo 90 Factorization, published in the September 2018 edition of the online International Journal of Vedic Mathematics. Note, link opens, PDF. To date, this site has attracted more than 106,157 absolute unique visitors, Google Analytics speak, from 11,124 cities and towns representing every country on Earth. Scores have returned repeatedly and not one has offered counterexamples. Commenting on LinkedIn.com, a NASA data scientist said of this work, "It is truly a well-thought-out labor of mathematical thought." From a hermeneutic perspective, the patterns explored herein speak eloquently for themselves. Res ipsa loquitur. 18 of the sequences discussed on this site have been published by the author on the online encyclopedia of integer sequences. Here's a link to them. OES listings for Gary W. Croft. Also, an MIT-licensed Python prime factorization tool compared 7 non-probabilistic, aka deterministic prime number sieving algorithms, and the programmer deemed the Croft spiral, aka Prime Spiral Sieve, the fastest and most efficient of those tested. Quoting the programmer, "The fastest method, Croft, is over 1,000 times faster than the slowest." Prime factorization algorithm speed test results. The Croft Spiral Sieve algorithm is listed under Python at Rosetta Code site devoted to prime decomposition, and can also be found posted on the University of Massachusetts Boston College of Science and Mathematics, Department of Computer Science server via this link, which opens a PDF. Further validation comes from Frederick Michael, PhD, Director, Experfy Institute, Harvard Innovation Laboratories, who utilized this site's period 24 model of primes and composites in a study of statistics and modular arithmetic of prime numbers. An abstract of the reference study can be found at Notes on Prime Numbers, their numerical statistics and patterns 1, modular arithmetic and the 8-fold period 24 model. The period 24 patterns in question relating to modulo 90 factorization algorithms and the digital root dyad cycles generated by twin primes are discussed at length on our page devoted to them. Factorization and prime number sieving algorithms and geometries. The sequence populating the prime spiral sieve pictured below can be variously defined as natural numbers co-prime to 30, that is, not divisible by 2, 3 or 5. And given no prime number, 5 is divisible by 2, 3 or 5. It's axiomatic that our factorization domain contains all prime numbers, 5 starting with 7, the number 1 being silent, and their multiplicative multiples beginning with 7x7 equals sign 49, the first composite number in the sequence. It follows that all members of our domain are relatively prime, aka co-prime or mutually prime, to 2, 3 and 5. Natural numbers 1, 7, 11, 13, 17, 19, 23, 29, modulo 30, which pass into 8 arithmetic progressions, each with a common difference of 30 between consecutive terms. Group U, 30, equals sign 1, 7, 11, 13, 17, 19, 23, 29, of positive integers smaller than and relatively prime to 30, with multiplication modulo 30. 1 plus 6 plus 4 plus 2 plus 4 plus 2 plus 4 plus 6 plus 2. Repeat. E. 30n plus 1, 30n plus 7, 30n plus 11, 30n plus 13, 30n plus 17, 30n plus 19, 30n plus 23, 30n plus 29. Natural numbers modulo 30 that distribute to the following 8 angles, all odd numbers with digital root of 1, 2, 4, 5, 7 or 8, and final digit of 1, 3, 7 or 9, the first 8 of which are 1, 7, 11, 13, 17, 19, 23, 29. Note, throughout this site, you'll find references to various cumulative sum and indexing formulae. For convenience, we've created a page dedicated to them, cumulative sum and indexing formulae. It's important to emphasize that the beautiful symmetries encountered within this factorization domain, both numeric and geometric, are largely a consequence of patterns rooted in its period 24 digital root, which has the following repetition cycle: 1, 7, 2, 4, 8, 1, 5, 2, 4, 1, 5, 7, 2, 4, 8, 5, 7, 4, 8, 1, 5, 7, 2, 8. Repeat. This 24-beat cycle is equivalent to 3 rotations around the prime spiral sieve. The first 24 members of our domain and their digital roots, therefore, are especially important given they set the initial conditions for all that follows. To emphasize this period, 8 mod 30 telescopic stretch to period 24 modulo 90. We occasionally group this sequence as N1, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 49, 53, 59, 61, 67, 71, 73, 77, 79, 83, 89, modulo 90. The modulo 90, period 24, digital root repetition cycle of our domain allows us to sieve and sequence by digital root, DR, as listed below and documented by the author on the online Encyclopedia of Integer Sequences. Dr. 1 equals sign n by 1, 19, 37, 73, mod 90, 1 plus 18 plus 18 plus 36 plus 18. Repeat, oes.org/A301617. Dr. 2 equals sign n 11, 29, 47, 83, mod 90, 11 plus 18 plus 18 plus 36 plus 18. Repeat, oes.org/A301621. Dr. 4 equals sign n 13, 31, 49, 67, mod 90, 13 plus 18 plus 18 plus 18 plus 36. Repeat, ois.org/A301622. Dr. 5 equals sign n 23, 41, 59, 77, mod 90, 23 plus 18 plus 18 plus 18 plus 36. Repeat, oas.org/A301623. Dr. 7 equals sign n 7, 43, 61, 79, mod d 97 plus 36 plus 18 plus 18 plus 18. Repeat, oas.org/A301628. Dr. 8 equals sign n 17, 53, 71, 89, mod 90, 17 plus 36 plus 18 plus 18 plus 18. Repeat, oes.org/A295869. when the modulo 90 matrix listed above is color-coded to highlight its 12 lateral 90 sums, 12x90 equals sign, 1080 equals sign, 360x3, perfect symmetry is exposed. Prime number digital root congruence matrix. In our section devoted to twin primes, we demonstrate how to configure the above table to sieve and/or sequence twin prime candidates by digital root dyads. Note, the easiest and fastest way to determine modulo 90 congruence of a whole number is to reduce all digits antecedent to the number's terminating digit to their digital root. For example, the first three digits of 2497 reduce to digital root 6, leaving 67, which equates to 2497, 67, not 90. Keep in mind that 9s count as 0 when calculating digital root. This is sometimes called casting out 9s. Below is a picture of the Prime Spiral Sieve showing rotations spanning numbers 1 through 259 of the infinite sequence populating the sieve as defined above. Prime number spiral sieve hidden deep within this sieve. A radical spin on modulo 30 wheel factorization are mysteriously beautiful symmetries and geometries profound in their implications. This sieve not only forms the basis of an extremely efficient and widely used prime number sieving algorithm of the non-probabilistic kind, which we provided links to above, but it demonstrates how prime numbers are distributed within a radial geometry that effectively defragments the Ulam spiral and ultimately leads us to the theory of everything. This domain, once fathomed, reveals itself to be a beautiful mathematical object. It can be conceived as both an infinite spiral and, when matrix factorized at the digital root level, an ever-expanding four-sided pyramid structured by palindromic sequences. Regardless, the real power of this geometry becomes evident when we triple it dimensionally and explore modulo 90 factorization symmetries at the digital root level, culminating in the magic mirror matrix, a calculatory geometry that serves as a prime factorization sequencer accounting for the first 1000 prime numbers, exactly, and ultimately all prime numbers. 5. Most profoundly, we'll discover how the 8 spiraling factorization algorithms, that is, the multiplicative multiples of the domain sequence starting with 72 that ultimately account for every composite number within the prime spiral sieve's orbits, are structured by rotational symmetry groups in the shape of equilateral triangles 1, 4, 7, 2, 5, 8, and 3, 6, 9. We'll demonstrate how these can be configured to form 3x3 matrices, which in turn extrapolate into beautiful complex polygons. Only elementary arithmetic and geometry are required to understand what you find on this site. This minimal requirement is reflected by Mazur and Stein in prime numbers and the Riemann hypothesis. It is striking how little you actually have to know in order to appreciate the revelations offered by numerical exploration. Foundations. Surprisingly, playing with arithmetic can lead us to unexpected and profound discoveries that point toward deeper mathematics and sometimes even deeper science. Pradeep Mutalik, PhD. The Puzzling Power of Simple Arithmetic, Quanta, April 20th, 2021. The genesis of most, if not all, repeating prime number patterns described in the mathematics literature, for example, twin primes, Cullen primes, Chen primes, sexy primes, cousin primes, Sophie Germain primes, Siamese primes, Cunningham chains. The list goes on, can be readily deciphered using the Prime Spiral Sieve as an analytical tool employing modular arithmetic and specifically modulo 30 relationships. Here are two examples supporting this claim, that is, using this sieve to analyze and predict Siamese primes, n2-2 and n2+2 are primes, and Sophie Germain primes, p and 2p+1 are primes, keeping in mind that these will make more sense after you have read what follows. The most obvious of these repeating prime patterns are the 3 twin prime distribution channels, described at length on this site. These and all other such repeating, albeit intermittent and seemingly random patterns are fundamentally sub-patterns of the set of natural numbers not divisible by 2, 3, or 5 when arrayed in 8 dimensions, whether in a matrix or spiral form. The illusion of randomness results from the overlapping sequences of the 8 algorithmic chord progressions that factorize the domain. We will be discussing these progressions when we get to prime factorization. The first rotation of the sieve, comprised of 8 members, 1, 7, 11, 13, 17, 19, 23, and 29, is the deterministic key to everything that follows. These are the first 8 counting numbers not divisible by 2, 3, or 5, a sequence which by definition includes, and only includes, 1 and all primes, 7 and their multiplicative multiples, and as you'll see below, it's conjectured that the entire set can be generated by a simple expression involving 2, 3, and 5. The inference of this conjecture is that all prime numbers greater than 5, that is, starting with 7, can be produced by this expression. Note, given our domain is limited to numbers 1, 7, 11, 13, 17, 19, 23, 29, modulo 30, only pi m equals sign 8/30 or 26.66% of natural numbers, n equals sign 0, 1, 2, 3 need be sieved. For example, to illustrate the proportionality of this ratio, we find that 25% of the first 100 natural numbers are prime, while 72% of numbers not divisible by 2, 3, or 5 are prime. And curiously, if we count 2, 3, and 5 in, after the fact we get 75%, or exactly 3 by 25%. Also note that if you plug the number 30 into Euler's totient function, phi 30 equals sign 8, with the 8 integers, known as totatives, smaller than and having no factors in common with 30 being 1, 7, 11, 13, 17, 19, 23, and 29, what are called prime roots above. 30 is the largest integer with this property. The integer 30, product of the first 3 prime numbers, 2, 3, and 5, and thus a primorial, plays a powerful role organizing the array's perfect symmetry, viz. In the case of the 8 prime roots, 1 plus 29 equals 30, 7 plus 23 equals 30, 11 plus 19 equals 30, and 13 plus 17 equals 30. In The Number Mysteries, well-known mathematician Marcus du Sautoy writes, "In the world of mathematics, the numbers 2, 3, and 5 are like hydrogen, helium, and lithium. That's what makes them the most important numbers in mathematics." Although 2, 3, and 5 are the only prime numbers not included in the domain under discussion, they are nonetheless integral to it. First of all, they sieve out roughly 73% of all natural numbers, leaving only those nominally necessary to construct a geometry within which prime numbers can be optimally arrayed. The remaining 26.66%, to be a bit more precise, constituting the array, can be constructed with an elegantly simple interchangeable expression, or power series if you prefer, that incorporates the first 3 primes. It's conjectured that this manifold series ultimately consists of all and only the numbers not divisible by 2, 3, or 5 and their negatives, which includes all prime numbers, 5, more below under the heading Conjectures and Facts relating to the Prime Spiral Sieve. What is critical to understand is that the invisible hand of 2, 3, and 5 and their factorial 30 create the structure within which the balance of the prime numbers, that is, all those greater than 5, are arrayed algorithmically, as we shall demonstrate. Primes 2, 3, and 5 play out in modulo 30, 60, 90 cycles, decomposing 2, 3, 6, 9 sequencing at the digital root level. Once the role of 2, 3, and 5 is properly understood, all else falls beautifully into place. Deep symmetries. Physicists have exalted symmetry to the position of the central concept in their attempts to organize and explain an otherwise bewildering and complex universe. Mario Livio, The Equation That Couldn't Be Solved, How Mathematical Genius Discovered the Language of Symmetry. The Prime Spiral Sieve possesses remarkable structural and numeric symmetries. For starters, the intervals between the prime roots and every subsequent row or rotation of the sieve are perfectly balanced, with a period 8 difference sequence of 6, 4, 2, 4, 2, 4, 6, 2. The entire domain can thus be defined as 1 plus 6 plus 4 plus 2 plus 4 plus 2 plus 4 plus 6 plus 2. Repeat. As we've already suggested, the number 30 figures large in our modulo 30 domain. The prime spiral sieve is Archimedean in that the separation distance between turns equals 30 ad infinitum. The first 2 rotations increment as follows. Root prime symmetry, involving 30s interestingly. The sum of the second rotation equals sign 360. The product of the first 3 primorials, 2x, 6x, 30 equals sign 360. And when you multiply the first 5 Fibonacci numbers in sequence, you produce 1, 2, 6, and 30. And speaking of the Fibonacci number sequence, there is symmetry mirroring the above in the relationship between the terminating digits of Fibonacci numbers and their index numbers equating to members of the array populating the prime spiral sieve. Fibonacci terminating digit symmetry. Remarkably, the sequence of Fibonacci terminating digits indexed to our domain, natural numbers not divisible by 2, 3, or 5, 13,937,179, see graphic above, is a prime number and a member of a twin prime pair, with 13,937,177. In case you're wondering, 13,937,179 is not a reversible prime, as the reversal is a semi-prime. 9,461 x 10,271 equal sign 97,173,931. However, given all the repunits that follow, we take note that both of the reversal's factors are congruent to 11, mod 30 and 90. Note, repunits are abbreviated ON, where n designates the number of unit 1s. Thus, 1 is R1 and 11 is R2. Perhaps most remarkable of all, 13,937,179 when added to its reversal, 97,173,931 equals sign 111,111,110. In strict digital root terms, the sum is 11,111,111, or R8, and the entire repeating and palindromic Fibo sequence end-to-end, equivalent to 2 rotations around the sieve, gives you this palindromic equivalency: 1,393,797,173,931, 11,111,111, mod 111,111,110. And interestingly, 11,111,111 times 111,111,110 equals 123,456,776,543,210. Another point of interest, the terminating digits of the first 8 Fibonacci numbers indexed to our domain, 13937,179, contain 2 each one. Yes, 3, S, 7, ES, and 9, ES. This is also true of the terminating digits of the first 8 members of our domain, 17137,939. Echoing the Fibonacci patterns just described, the terminating digits of the prime roots, 17,137,939, when added to their reversal, 93,973,171, equal sign 111,111,110. And note that 111,111,111 asterisk 111,111,110 equal sign 1, 2, 3, 4, 5, 6, 7, 8, 8, 7, 6, 5, 4, 3, 2, 1, 0. Yet another related dimension of symmetry, the terminating digits of the prime root angles, 24,264,868. See illustration of Prime Spiral Sieve when added to their reversal, 86,846,242. Equal sign 111,111,110. Not to mention, this sequence possesses symmetries that dovetail perfectly with the prime root and Fibo sequences. And when you combine the terminating digit symmetries described above, capturing 3 rotations around the sieve in their actual sequences, you produce the ultimate combinatorial symmetry, terminating digit symmetries. Here's yet another fascinating dimension of symmetry, the pattern of 9s created by decomposing and summing either the digits of Fibonacci numbers indexed to the first 2 rotations of the spiral, a palindromic pattern, 13937179997, 173931, that repeats every 16 Fibo index numbers, or similarly, decomposing and summing the prime root angles. The decomposition works as follows. In digit sum arithmetic, this would be termed summing to the digital root. F17, the 17th Fibonacci number, equal sign 1597 equals 1 plus 5 plus 9 plus 7 equals 22 equals sign 2 plus 2 equals 4, Fibonacci and prime root angle terminating digit symmetries. Another dimension of symmetry involves the terminating digits of the prime roots and their angles. those paired with like terminating digits being separated by 120 degrees, 1, 12 degrees, and 11, 132 degrees, 13, 156 degrees, and 23, 276 degrees, 7, 84 degrees, and 17, 204 degrees, 19, 228 degrees, and 29, 348 degrees. Another consideration with regard to terminating digits is that one can easily construct, by combining all numbers with the same terminating digits, a four-fold arithmetic progression in increments of plus 10 and plus 20, starting with 1, 7, 13, and 19. Thus, combining 1, 12 degrees, and 11, 132 degrees gives us 1, 11, 31, 41, 61, 71, 91, plus 10 plus 20, and combining 7, 84 degrees, and 17, 204 degrees gives us 7, 17, 37, 47, 67, 77, 97, plus 10 plus 20, n, combining 13, 156 degrees, and 23, 276 degrees gives us 13, 23, 43, 53, 73, 83, 103, plus 10 plus 20, n, and combining 19, 228 degrees, and 29, 348 degrees, gives us 19, 29, 49, 59, 79, 89, 109, plus 10 plus 20. Looking at the array in this configuration, however, has borne no fruit. As fascinating as the symmetries examined above may be, they are but a prelude to the beautiful patterns we'll explore when we discuss digital root sequencing and the trinity of triangles and magic squares rooted in Vedic arithmetic that drive factorization algorithms within this domain. And finally, if you want to jump ahead and view the perfect palindromic symmetry found at the heart of factorization, check out the magic mirror matrix that maps factorizatons at the digital root level and accounts for the first 1,000 prime numbers exactly. The Prime Spiral Sieve. Around the perimeter of the spiral sieve, pictured below, you'll note that the 8 radii are labeled in relation to their modulo 30 prime roots. That is 1, 12 degrees, 7, 84 degrees, 11, 132 degrees, 13, 156 degrees, 17, 204 degrees, 19, 228 degrees, 23, 276 degrees, and 29, 348 degrees. These relate to the fact that the circle is segmented into 30 equal sectors, or radii, separated by 12 degrees, 30 asterisk 12 degree equal sign 360 degree. Although only the 8 radials that are the focus of this study are shown, Prime Spiral Sieve. This sieve exposes the twin primes aligning as they do along 3 distinct distribution channels. One obvious implication is that those numbers in the array congruent to 7 modulo 30, radial angle 84 degrees, and 23 modulo 30, radial angle 276 degrees, can be excluded as twin prime candidates and, by definition, all prime numbers distributed along these 2 diagonals, with the exception of 7, which is twinned with 5, will be what are known as isolated primes. Later we explain how twin prime candidates can be segregated from all other positive integers and be partitioned into 3 columnar sets covertly aligned by the first 3 prime numbers, encoded in angles. Conjectures and facts relating to the Prime Spiral Sieve. The array is rooted in the first 3 prime numbers, 2, 3 and 5, and their product, 30, the third primorial. This array reveals that the first 3 primes play a very special role in creating the symmetrical geometries that align the distribution of all subsequent prime numbers, thus distinguishing them from all other primes. Primes 2, 3 and 5 are like 8-legged spiders assigned to spin the beautiful spiraling web in which the remaining prime numbers are arrayed along assigned threads. For a detailed listing of number 30's attributes plus reference links, click here, the number 30. It is conjectured that all and only the numbers in this array and their negatives can be derived using the interchangeable expression incorporating the first 3 prime numbers, 2, 3 and 5, where x equals sign 2, y equals sign 3, and z equals sign 5. Thus, x noi n da zn, x and zn plus yn and in zn psi xn. For example, 2, 5 minus 33 equals 13, 32, 3 minus 2 equals 73. This expression, therefore, potentially generates all numbers not divisible by its 3 terms, 2, 3 and 5, including all prime numbers. 5. Note, For any given number in the array, there are multiple and possibly an infinite number of solutions. For example, the number 11 can be expressed as x to y plus z equals sine 11, x to y 2z2 equals sine 11, z2 yx6 equals sine 11, etc. More examples below. 2, 3, 5 in combo, equal sign n not div 2, 3, or 5. All prime numbers, with the exception of 2, 3, and 5, are distributed along 8 diagonals in intervals of 30, starting with prime roots. 1, 7, 11, 13, 17, 19, 23, and 29. Thus 1, 31, 61, 91, 7, 37, 67, 97, n, etc. The products of any combination of factors in the array equals sign a number in the array. For example, 7 11 times 13 equals 1001, etc. Conversely, all factors for composite numbers in the array can be found in the array. Every composite number in our modulo 30 domain can be derived from the product of two terms in the domain multiplied together, and these multipliers need not necessarily be prime themselves. For example, 5831, which is congruent to 11 modulo 30 and therefore in the array, is the product of 49x119 equal sine 5831. In this example, neither 49, 7x7, nor 119, 7x17 are prime, though both are members of the array. The sum of any sequential odd number of addends in the array equals sign a number in the array. For example, 1 plus 7 plus 11 equals sign 19, 1 plus 7 plus 11 plus 13 plus 17 equals sign 49, etc. Because the digital roots of all prime root angles are either 3 or 6, any prime root angle times another will produce a product whose digital root equals sine 9. For example, PR7, 84 degrees, x PR29, 348 degrees equals sine 84, x 348 equals sine 29232 equals sine Dr. 9. Any number in the array, x 30 plus 1 equals a number in the array. The sum of the angles for 2, 24 degrees, 3, 36 degrees, and 5, 60 degrees, equals sine 120 degrees, and the sum of the prime roots, 1 plus 7 plus 11 plus 13 plus 17 plus 19 plus 23 plus 29, also equals sine 120. This is because the prime roots are an arithmetic anagram for the angles of the first three primes. Thus, 11 plus 13 equals 24, 17 plus 19 equals 36, and 1 plus 7 plus 23 plus 29 equals sine 60. The sum of the second rotation equals sine 360, 3 224 degrees plus 336 degrees plus 560 degrees equals sine 30,360 degrees. The array reveals beautifully symmetrical relationships. Mod 30 of all numbers in this array, and thus all primes other than 2, 3, and 5 must be 1, 7, 11, 13, 17, 19, 23, or 29. The sum of the digital root sums of the prime roots, 1, 7, 11, 13, 17, 19, 23, 29, equals sine 1 plus 7 plus 2 plus 4 plus 8 plus 1 plus 5 plus 2 equals sine 30. This sieve reveals why all primes, 5 are adjacent to a multiple of 6, as the prime root radii are adjacent to 6, 72 degrees, 12, 144 degrees, 18, 216 degrees, 24, 288 degrees, and 30, 360 degrees. And you'll note that the digital root sums of all adjacent angles equal 9. The modulo 90 congruence of any member of this domain can be determined by digital root and terminating digit configured in an XY matrix, arrayed by digital root 1, 2, 4, 5, 7, 8 on the vertical axis and by terminating digits 1, 3, 7, 9 on the horizontal axis. Take, for example, number 179, which happens to be prime. Its digital root equals sine 8 and its terminating digit equals sine 9. Looking at the table below, we can quickly determine that 179 is congruent to 89 modulo 90. By definition, prime factors for all composite numbers within this domain must originate from within it, which is why all composite numbers are reducible to one or more modulo 90 congruence dyads, traceable to the first 24 members of this domain. Modulo 90 congruence determined by digital root and terminating digit factorization and sieving methods. employing the Prime Spiral Sieve for a detailed discussion of efficient factorization and prime number sieving algorithms, as well as an in-depth analysis of the 8-chord progression and deterministic modulo 90 digital root dyad sequences underlying all factorizations employing this sieve. Click here, Factorization and Prime Number Sieving Algorithms. If you use Python, the computer programming language designed for the development of scientific engineering and mathematics applications, and want to cut to the chase, check out the MIT licensed Python module dubbed PyPrimes. It's designed to speed test non-probabilistic prime number sieving algorithms, that is, deterministic sieves, that precisely account for all prime numbers within a given range. These include the Sieve of Eratosthenes, wheel factorization, and the Prime Spiral Sieve, referred to by its alternative name Croft Spiral Sieve or simply Croft Spiral, here at code.google.com. The programmer, we're pleased to report, rates the Prime Spiral Sieve fastest best and recommends it as the preferred way of generating prime numbers compared to the several sieves tested, counting primes. The Prime Spiral Sieve can be used to calculate the number of prime numbers within a stated range, from 0 to n or px using the standard notation, with absolute precision, albeit in several unconventional steps. It does so by employing the 4 elementary operations of arithmetic: addition, subtraction, multiplication, and division, and extracting one's square root. You could say that this approach is more recipe than function algorithm or asymptotic analysis. Regardless, what makes this method novel is that it parses and gives the number of primes without the need to identify any specific primes other than the first 3. 2, 3, and 5, that is. There's no requirement for primality testing per se. For an in-depth exploration of this methodology, click here. Prime number counting methodology, twin primes. The world of twin primes is truly magical. For a detailed discussion of the factorization algorithms and symmetry groups, permutating matrices, orthogonal Latin squares, palindromes, equilateral triangles, complex polygons, etc., that ultimately determine the distribution of twin primes along 3 modulo 30 channels, go to this page. Twin Primes Demystified Distribution Algorithms and Symmetries. There you will be introduced to the beautiful palindromagon, pictured below, a complex polygon generated by tiered digital root dyad cycles central to the twin prime distribution channels, as well as modulo 90 factorization sequences. Its name comes from the fact that the triangulations generating it sum to a period 18 palindrome consisting of the 6 possible permutations of 3, 6, 9, which in turn can be permutated to produce 2, 3x3 Latin squares with rows, columns, and principal diagonals, all summing to 18. Palindromagon distribution of perfect squares. All the perfect squares within our domain, numbers not divisible by 2, 3, or 5, possess a digital root of 1, 4, or 7, and are congruent to either 1 or 19 modulo 30. By definition, this includes the squares of all prime numbers greater than 5. We can easily explain this from a digital root perspective, given that the digital roots of members of our domain are restricted to 1, 2, 4, 5, 7, or 8. Numbers with digital root 3, 6, or 9 can't be members because they are divisible by 3. Thus, the digital root of squares is likewise restricted as follows, and note the palindrome. 1x1 equals sign 1, 2x2 equals sign 4, 4x4 equals sign 7, 5x5 equals sign 7, 7x7 equals sign 4, 8x8 equals sign 1. By arithmetic law, perfect squares can only have terminating digits of 1, 4, 5, 6, 9, or 0. Only 2 of these final digits, 1 and 9, apply to our domain, that is for numbers congruent to 1, 11, 19, or 29, modulo 30. In turn, numbers congruent to 11, 29 sequence digital roots 2, 5, or 8, and therefore, as we demonstrated above, there can be no perfect squares among them. And so it is that the distribution of squares is narrowed to numbers congruent to #1, 19 modulo 30, which is to say they distribute along 2 and only 2 radii of the prime spiral sieve. 12 degrees, numbers congruent to 1 modulo 30, and 228 degrees, numbers congruent to 19 modulo 30. This is also consistent with the fact that the quadratic residues for modulo 30, making them congruent with perfect squares, are 1 and 19. and it follows that all squares in this series distribute evenly to 2 of the 3 twin prime distribution channels described above, negating a significant percentage of potential twin prime pairs. The matrix below illustrates the distribution of squares from 159 squares highlighted in blue, distribution of squared members of domain, summarizing the above relationships in mathematical terms and in the knowledge that these modular relationships apply to the squares of all prime numbers. BOS is 7. We get, for all En, where n mod 30 equals sine 1 and 2 mod 30 equals sine 1 for all, and where n mod 30 equals sine 29 and 2 mod 30 equals sine 1 for all, n where n mod 30 equals sine 11 and 2 mod 30 equals sine 1 for all, n where n mod 30 equals sine 19 and 2 mod 30 equals sine 1. When the digital root of perfect squares is sequenced within a modulo 30x3 equals sine modulo 90 horizon, beautiful symmetries in the form of period 24 palindromes are revealed, which the author has documented on the online encyclopedia of integer sequences as digital root of squares of numbers not divisible by 2, 3, or 5 at 24,092. 1 4 4 7 1 1 7 4 7 1 7 4 4 7 1 7 4 7 1 1 7 4 4 1. In the matrix pictured below, we list the first 24 elements of our domain. Take their squares, calculate the modulo 90 congruence and digital roots of each square, and display the digital root factorization dyad for each square, and map their collective bilateral 9-sum symmetry. Perfect squares repeating digital root palindrome. Here's one more modulo 90 spin on perfect squares. Passing the squares by their mod 90 congruence reveals that there are 96 perfect squares generated with each 360 equals 40 times 432. Much more on the significance of number 432 elsewhere on this site. Here's the graphic. 96 perfect squares per 4x90 equals sine 360-degree cycle. Before leaving the subject of perfect squares, there's another hidden dimension of our domain worth noting involving multiples of 360, that is, when framed as 1, 7, 11, 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 49, 53, 59, 61, 67, 71, 73, 77, 79, 83, 89, modulo 90, and taking bipolar differentials of perfect squares as follows: 892, 12, equals sine 360 x 22, 832, 72, equals sine 360 x 19, 792, 112, equals sine 360 x 17, 772 time 132 equals sine 360 x 16, 732, 172 equals sine 360 x 14, 712, 192 equals sine 360 x 13, 672, 232 equals sine 360 x 11, 612, 292 equals sine 360 x 8, 592, 312 equals sine 360 x 7, 532, 372 equals sine 360 x 4, 492, 412 equals sine 360 x 2, 472, 432 equals sine 360 x 1 from alpha to omega. Not every beautiful theory has a physical application, but all fundamental physical theories found so far, without exception, have a type of beauty or symmetry. Michio Kaku, the God equation. The Ulam spiral arrays prime numbers in fragmented spiral and diagonal formations, quoting from Wikipedia. Since in the Ulam spiral adjacent diagonals are alternatively odd and even numbers, it is no surprise that all prime numbers lie in alternate diagonal. What is startling is the tendency of prime numbers to lie on some diagonals more than others. From this one might deduce that the Ulam spiral is very likely a scrambled version of the Prime Spiral Sieve, as the latter demonstrates how all prime numbers, except 2, 3, and 5, are fundamentally arrayed along 8 and only 8 diagonals. It would appear, circumstantially, that the Prime Spiral Sieve is mathematically harmonious and perhaps isomorphic with the most complex and visually arresting Lie group named E8, which, like the Prime Spiral Sieve, is 8-dimensional. E8 is pictured below, superimposed with a star polygon and the 8 radii of the modulo 30 factorization wheel. This group was recently in the news as possibly being a key to unifying theories in gravity and particle physics to create the proverbial theory of everything. The number 30, integral to the Prime Spiral Sieve, is the Coxeter group number H, dual Coxeter number, and the highest degree of fundamental invariance of E8. You'll note, looking at the graphical representation of E8 below, that the perimeters of every one of its multiple concentric circles possesses 30 points, and not surprisingly, E8 has 2, 3, and 5 torsion, and its exponents are the coprimes up to 30, that is 1, 7, 11, 13, 17, 19, 23, and 29. Numbers you're very familiar with if you've read to this point. Which brings us full circle Omicron graphic, superimposes E8, star polygon, and mod 30. Factorization wheel radii, the number 30 in Lie group E8. This graphic superimposes images of the star polygon, modulo 30 wheel factorization radii, and E8 graph of the Gosset, 421 polytope as a two-dimensional skew orthogonal projection inside Petri polygon. An emulation of the hand-drawn original by Peter McMullen, licensed by Creative Commons, license terms here, for 3D version of this graphic step back 3 feet from the screen. We'll close with a graphic showing E24 superimposed with the 24 radials of a modulo 90 factorization wheel and the 15 points of a 15-point star represented with red dots, each point separated by 24 degrees, and we see that all 9 twin prime distribution channels are hit dead center.